Distributed architectures is what some of the most advanced IT shops are striving to achieve. Building distributed OpenShift platform on Baremetal gets us additional resiliency, flexibility, and scalability of our infrastructure. In this video, I'll explain why you might want to consider breaking up your monolithic OpenShift platform and how to do it in a relatively easy way. We're going to use my favorite agent-based installer for OpenShift to achieve that. By the end of this video, you should be equipped with the knowledge to build your own virtual private cloud with multiple availability zones and failure domains. You might remember from one of my previous videos this standard architecture. I have broken down the controllers and workers monolithic boxes to better demonstrate the issue. In this example, we got 3 controllers on one side and 3 workers on the other, all connected to the same layer 2 network. In the traditional deployment, we need to put them on the same layer 2 network in order to manage their virtual IPs with VRRP mechanism, also known as Keep Alive D. It is an uncommon scenario, but what if one of your workers becomes a noisy neighbor, or even worse, creates a network loop or other network storm generating event? In reality, it doesn't have to be this worker. Anyone connected to the same layer 2 might cause you a grief. Since they are all connected to the same pipe, the rest of your infrastructure would most likely go down with it. Yes, OpenShift is capable of recovering from such scenarios, but nevertheless, it will take time and service disruption to your end users. Introducing OpenShift Baremetal Distributed Architecture. This concept has been available for ages on public clouds, but it's relatively new for Baremetal. In this model, we group our controllers and workers into 3 availability zones, or failure domains. There's 1 controller and at least 1 worker per AZ. Of course, you can scale out workers as your heart desires. Each availability zone is connected to its own router. Could be a leaf switch pair or network fabric. Also, each controller runs in its own layer 2 network. We still need to take care of the virtual IPs that service our Kubernetes API and Ingress controllers. In my example, I'm pushing them to a dedicated highly available load balancers. Now, let's go over our failure scenario. Worker 2 gets all fussy and creates a network storm. In this architecture, he only takes down the controller in the same availability zone, and since OpenShift is highly available, there's no impact to the end users. The recovery is also much easier since the failure has been isolated to a single zone. If you are not a fan of the dedicated load balancers, there's also a way to push the VIPs management to a BGP agent running directly on your OpenShift nodes using MetalLB operator. For a Baremetal deployment, this is a day 2 option, but it goes beyond the scope of this video. I will leave the BGP example in the comment below. But please know that BGP option is not currently supported and would require a support exception. Now we understand the whys and hows. Let's dive into the implementation. Let me start by showing you my external load balancer configuration. I am lucky to have access to enterprise-grade hardware load balancer in my lab from Fortinet. If you're not as lucky as me, the free HA proxy would do the trick, and I'll share the sample config for that in the video description. Since I'm using the agent-based installer, let's look at my agent config YAML. Please note that each controller is running in its own layer 2/24 subnet. Same goes for the workers, 1 in each availability zone. With the install config, I'm making 2 changes out of the standard configuration. First, my machine network has to cover all the availability zones, so I'm including /16 supernet. Second, the platform needs to be set to none. You can see that I'm also including load balancer type user managed. However, that variable is only available when using the IPI. Nevertheless, this is all we need to do during day 1 configuration. Let's generate the ISO images and boot the Baremetal nodes. The rest of the installation is generally the same as standard. If you want to see more details, check out my other basic installation video with agent-based installer that goes a bit slower pace and with more details. Once the deployment completes, you can verify that each Baremetal node lives in its own L2 network. Now, this next step is recommended if you're planning to deploy a larger cluster and you are also using OpenShift Data Foundation as your software-defined storage. I'm going to tag each of my hyperconverged worker nodes with a topology tag, which will enable ODF awareness of my multi-zone infrastructure. Next, I'm installing ODF with all its prerequisites. For more information on that topic, check out my yet another video, also linked in the description down below. Once the storage installation is complete, I'm going to enable a debugging tool for it and verify my OSD drives have been placed in the correct AZ buckets. Since I am only using 3 hyperconverged nodes in this lab, this will not really make much difference, but the purpose of this setting is to ensure availability of the data replica in each failure domain for higher resiliency. As a bonus, you might also create machine config pools that would separate your workers and give a bit more control over how the net new configuration gets applied to your cluster. Here is the example I applied in my environment. First, label the worker nodes with appropriate availability zone, then create machine pools for each of them. After a few minutes, the new MCPs gets rendered and you can verify that each has its own pool of Baremetal workers. The OC get nodes will also show them in their AZs. This is all in a nutshell. The few gotchas to keep in mind: for the internal ODF storage, you can no longer use dedicated MAC VLAN networks for storage front-end and back-end. The overlay networks can still stretch across the availability zones, so that might be a good alternative. When creating additional VLAN-based networks, you might consider attaching them to its availability zone. For example, VLANs available in AZ1 should not be used in AZ2 or AZ3. Finally, this architecture really makes sense if you combine it with BGP-based dynamic networking. That's another topic I'm planning to cover, but maybe in another video. Let me know in the comments down below if you're planning to use this architecture. I have noticed on my other videos that folks like to ask questions and collaborate on topics described in these videos. Let's make this a theme of a channel and help each other out. I hope this video has been helpful, and thanks for watching.